All right, so over on page 466, we have a brand new formula. A sub t equals A sub 0, which we're going to call A naught, times E raised to the kt power. All right, so this A sub t means the amount after a period of time. A naught means the initial amount, how much we start with. E is that number that we found when we put in e to the first power, 2.71828 or something like that. K is a constant that's going to change with every problem. We'll end up solving for that first. And T is the amount of time elapsed between this and this. All right, so I think for each one of these problems that they're going to give you, maybe not. I thought maybe they gave you the equation, but it doesn't look like they do. So you need to memorize this equation right here. Okay, AT equals A naught times E raised to the KT power. So if you look on page 466 at 115.2, the problem reads, in the beginning there were 400 bacteria in the dish. So that's the initial amount. That's what we start with. The number of bacteria increased exponentially 3 days later. So that's the amount of time that's elapsed. So that's T. 3 days later, there were 2,000 bacteria in the dish. So yeah, it's increasing. So it wants us to find out how many bacteria there would be in 8 days. So in order to do that, we've got to solve for K. So the first thing we'll do is divide both sides by 400. Right, so we get e to the 3k equals, that cancels, and 20 divided by 4 is 5. Now with the last problem we had a base of 10, and so we took the log of both sides. This time we have a base of e, so we're going to take the natural log, or ln, of both sides. This will be ln of 5 is equal to ln of e to the 3k. So what happens to the ln and the e? That's right, they cancel. So we have 3k is equal to ln of 5. And then if we divide both sides by 3, we have k is equal to ln of 5 divided by 3. And that's ln of 5, not 5 divided by 3. So now let's do that in the calculator so we get a value here for k. All right, so I went ln 5, close the parentheses, and divide that by 3. So there's our k. I'm just going to put this on top so we can just see it. All right, so k is 0.5365. And I'm going to remember that much of it because the calculator's doing the work, guys. And the more places that we leave in the decimal places that we leave in there, the more accurate our answer will end up being. All right, so we've got k. So now we go on. We have AT equals, the initial amount was 4, doesn't change. E to the 0.53, oops, 5365 t. There's my equation. If it asks me for the exponential equation, there it is. So now, if they asked us to find how much time it took for the bacteria to grow to something, we could find it. In this case, it wants to know how much bacteria there is after 8 days. So we plug in 8 for t. All right, so in the calculator, I'm going to multiply 0.5365 times 8. So I have a sub t equals 400 times e raised to the 4.292 power. Now let's do that in the calculator and see what we get. So I need 400, and to bring up that e, remember we have to hit second ln, and what was that? 0.5365, I believe is what we had. I can't see it. And enter. So we get 400 times e. Oh, I forgot to multiply it times 8. Okay, so let's go back. 400 second ln of the 0.5365 times 8, because I can't remember what that number was. And we get 29,245. So let me take a picture of that. And then if we didn't use the right numbers, I'll go back and do it again. But that's the process that you use. Okay, so it was, yeah, that's right. All right, so that was 0.5365 times 8. So the answer is 29,245. Now that's different than what the book has. So why would you think that it would be different than what the book has? Well, we rounded off the k to be 0.5365 instead of 0.537, which is what they did. So whose answer is more accurate? Like always, ours is more accurate because we carried more decimal places. And that's what you want to do. The calculator did the work. It's not going to hurt you to carry an extra decimal place in there to make it more accurate. Okay, so let's do another one. This is on page 467. It says, in the beginning, there were 4.25 ounces of radioactive material. It decayed exponentially, thank goodness. 10 years later, so our time is 10. 10 years later, there's 3.92 ounces. Guys, it took 10 years for it to decay from 4.25 ounces to 3.92. That's a very, very slow process. That's why it's so important for radioactive waste to be disposed of properly, because otherwise people in the future could get really seriously hurt or become very, very ill by running into it or being exposed to it. This is a very slow process. All right, so it's asking us here, how much would remain after 30 years? So the first thing we need to do is find the constant, and then we'll plug in 30 for t. So if you remember, we divide both sides by 4.25, and that'll cancel out. So I'm going to go ahead and take 3.92, you can do this on your calculators, divided by 4.25. And I get 0.92235. I'm going to leave that number in the calculator anyway. The whole thing is equal to e to the 10k. And then how do I get rid of the e? I take the natural log of both sides. So I'm going to take ln of this thing. And ln of this. And here, this will cancel out. So I have 10k is equal to the ln of this, which we'll do in the calculator here in just a minute, because I already have that number in the calculator. And then we'll just divide that by 10, and that will be our k. All right, so let's see what that comes out to. So all I've got to do is take the natural log of this answer that I have in here. So ln of second answer, so it brings in what I've got, close the parentheses, and then divide that by 10. So that's going to be our constant. So that's and that's different from what we've gotten in the past. It's a negative 0.00808. It's negative. Why do you think it would be negative? None of the rest of them have been negative. It's negative because this decreases. It decreases from the 4.25 to the 3.92. So it is a decrease. Anytime you have an exponential decrease, your constant will be negative. Constant will be positive if it's an increase. Constant will be negative if it's a decrease. All right? Okay, so now we're going to have AT equals, A naught was 4.25, e to the negative 0.00808 t. And the t in this case is going to be 30 because they want to know how much will be left 30 years from now. All right, so let's put that in. AT will be equal to e to the negative 0.00808 times 30. All right, and I've got that number in the calculator, so what we'll do is we're going to take 4.25 and then second ln of that answer, so that'll be second ans times the time is 30. Maybe I don't need to close the parentheses there. Let's see what it says. All right. So we get 3.34. Gosh, it just hasn't gone down by very much at all. Oops. So the amount after 30 years is 3.335. So guys, we started out with 4.25 initially. After 30 years, we still have 3.335 ounces of this thing. So you can see how radioactive material just does not decay very quickly. It's super important that we take good care of it. All right, the next part is talking about money. Everybody likes to talk about money, okay? So the equation that we use for interest is the amount after a period of time is equal to P, or principal. That's the amount that you deposit in the bank, times E raised to the RT. R is the interest rate. T is the time, like it was before. P is the amount that you deposit. It's called the principal. Now, the one thing that's super important here is that you must enter the interest rate as a decimal. If it says that you're going to invest at 2.5%, then your R is going to be 0.025, right? If it's 5.7%, your R will be 0.057. If you don't change it to a decimal, guys, it's going to make it look like you're making so much money, and you won't be, all right? So make sure before you plug anything into this equation that you change the interest rate to a decimal. And you are going to have to remember this formula. So on page 468, 115.4, it says Roger deposited $5,000. That's his principal, so that goes here for P. And then it says in an interest-bearing account that paid 7.5%. So that's 0.075. That's the interest rate, 7.5%. Compounded continuously. That means that the interest is calculated continuously. That's the only kind we're going to deal with right now, is compounded continuously. There's a different formula for if it's compounded quarterly or weekly or monthly or semi-annually. This is compounded continuously. Okay, oops, sorry. Oh my goodness. All right. And now it says, how much money did he have in 10 years? So T, this T right here becomes 10. So this is all in the calculator. All right? To make myself a note so I don't forget what I'm plugging in. 5,000 E to the 0.075 times 10. Well, what is 0.075 times 10? Just moves the decimal over one place, right? So it's actually going to be multiplied by 0.075. All right, so we're going to have here 5,000 second ln of 0.075 times 10, or 0.75, whichever way you want to do it. 0.75, all right. So there's how much money we'll have at the end of 10 years. That's not too bad. But I'm telling you right now, guys, you're not going to find, you won't find an interest rate like that now or probably any time in the near future. So if you can find it, I'd grab it, but it's just, oh, that's the wrong one. Okay, so that value was $10,585 and no cents. All right, so basically, we a little bit better than doubled our money, didn't we? We started with $5,000 and now we have $10,585. The book rounded it off to the nearest hundred. It doesn't tell us to do that, so I would just leave it as what we get out of the calculator, dollars and cents. All right, lots of good stuff today.